Hey everybody, we're going to go ahead and step into our third friction-related problem. There's a lot of things that are going on in this problem, but we can break it down and make sense of it as we go. De-guess is a helpful tool to this, but there's also some asides that you're going to need to think about where if things are not in the exact same or correct values that you want, sometimes we have to do a little kind of work on the side in order to get them there. And sometimes that work on the side takes a little bit of room. So I'm going to work in the margins a little bit on this problem as things go. And you'll see that over here. I'm going to start out here by kind of highlighting some of the most important pieces, making sure that we've got what we need. It starts out on the problem and it says, if a 1,500 Newton force is exerted, meaning this is my push, is exerted on a 200 kilogram crate. Keeping in mind, that's not force, this is mass. So we might be alerted at this point to be able to say, oh, I need to figure out what my gravitational pull is, my weight. And it says to cause it to move across the floor. If the coefficient of friction is 0.25, right here, what is the crate's acceleration? Now, here's the biggest deal here. This acceleration is a big indication that if there is an acceleration, it means that the sum of all the forces is not going to be zero, because in order to get an acceleration, we need some sort of unbalanced force. So that's an important one. So I'm going to annotate a little bit further up here and put in some values to help me out. This 1,500 Newton force is what I'm pushing. So I'm going to go ahead and just drop in this F applied, or F app. So that's my 1,500 newtons. This 200 kilograms is not a force, it's a mass. So I'm going to put this in as my mass, and that's important to note. My coefficient of friction is this number right here. So I'm going to go ahead and slide in my coefficient of friction. And then acceleration, I'm going to put that in as the letter A. So I've kind of annotated my problem, which is really important to try and understand these things. The other thing that I'm going to take note of on the side is that I'm going to go ahead and draw on a few formulas over here of things that I have to work with. One of the formulas that I have to work with here is Newton's second law. Newton's second law is F equals ma. I know that I've got this to work with. I've got forces, masses, and acceleration, so that's probably going to come into account here somewhere. The other one is that because I have a mass here, and I know that I'm going to be talking about the forces of gravity, I'll probably need the idea of weight. And the equation for weight is just Newton's second law, but with a specific acceleration, because all objects on Earth get pulled downwards with a particular force that causes them all to accelerate at a certain number. And that number here is always the same for all objects, regardless of their mass, which is 9.8 meters per second every second. This number is always known. All right, so I've got a couple things that are working out here. There's one more equation that I've got that I can work with, which is the equation of the coefficient of friction, which is the force of friction divided by the normal force. All right, so I've got three different equations to work from and to use as a tool. And I've got a lot of stuff annotated in the problem up here. So the next step in my process is I'm going to go ahead and start drawing a free body diagram to help me out. All right, in this case, we're talking about a crate, but my crate looks oh so beautiful. There's my crate. Isn't it gorgeous? So crate, C-R-A-T-E. Good. And then I'm going to go ahead and draw on the forces that are a part of this. One is that force of gravity that exerts on all objects that are here. And let's say that this crate is moving across the floor, because that's what it says in the problem. So I'm going to go ahead and draw on the floor so that I have something to think about here. If the force of gravity here is down, then there is a force of the floor pushing up. And it's going to be equal and opposite. These ones are going to be balanced. In the y direction here, they're going to be balanced. And I know that because it's not getting sucked into the floor. It didn't tell me it's getting sucked into the floor. And it's not being thrown off of the floor. So the up and down motion of the crate is nothing. So my normal force and my gravitational force are balanced. On the flip side of things, it does say that there's an acceleration, which I'm going to assume is in the x direction here along the way. And so I'm going to put in a couple forces here. One of those forces is my applied force, right? My force applied. Now, my force of friction can never be greater than my applied force. It just doesn't work that way. It can be less than, but it cannot be greater than. So let's go ahead and put in a frictional force. And because there's an acceleration, I'm going to put this in as showing me less. So I'm going to say that this is my force of friction. Now up above, it told me a few things, and I could write them into my problem here so that I know what I'm talking about. I know that I'm pulling with a 1500 Newton force here. So this is 1500 Newtons that I'm pulling with. Is my force of friction going to be 1500 Newtons? Answer, no, if there's an acceleration. Now, if it was 1500 Newtons, if it was exactly the same, then the acceleration would be 0. I don't know if it is because it says what's the acceleration. I'm going to leave it. Do I know my force of gravity or my normal force? The answer is I don't yet, but I do know the mass of the crate, which is going to be helpful to me. So this is where I can go ahead and kind of do this aside calculation to help me out, where I can say, I want to know what the force of gravity is. And the force of gravity is equal to the mass of the crate times the acceleration due to gravity. Careful, this is not a force, it's an acceleration. So I'm going to plug in the things that I know, and I know that I've got 200 kilograms. And I'm going to multiply that now times my acceleration due to gravity, which is 9.8 meters per second squared. Now, if 9.8 was exactly 10, the answer would be 2,000. Even it kind of looks like 2,000. There's a decimal there. But it's going to be slightly less than 2,000. So if I plug that into a calculator, I end up getting 1,960 newtons. 1,960 newtons is my force of gravity. That's my weight right here. And I can start to plug that in if I want to. So I can come down here and say 1,960 newtons is my weight. Now, recognizing that because gravity is pulling it down and the floor is pushing up and that there's no motion kind of up and down here, I'm going to go ahead and put the exact same number here, 1,960 newtons. And I'm going to put that in for my normal force as well, equal and opposite. So now I have a pull of 1,500 newtons. These two are balancing each other out, and I need to figure out what the force of friction is. Luckily, I have that tool as well in my toolkit because I've got this equation over here on the side of the force of friction and the normal force. So let's go ahead and plug that one in. Maybe I'll kind of put this off to the side. You're like, well, that's kind of scratch work. And the next piece to this is that my coefficient of friction is equal to the force of friction all over my force that is normal. We want to solve this for the force of friction. And so right now it's not, but this is an easy one to change over. I've done it before, and I can go ahead and I can multiply on both sides the force that is normal, just like you would in algebra, right? Whatever you do to one side, you do to the other side. And on this side here, the normal forces cancel out, and I'm left with it over there. And if I rework the problem and turn it around to say the force of friction is equal to the normal force times the coefficient of friction. That's not a very good coefficient of friction. That's better, a little bit. Do I know these things? And yeah, I actually do. I can plug them in, right? I can plug in exactly what I already know. So I'm going to go and do that right now. And I'm going to say that my normal force, which is the 1,960, which is coming from the weight, right? The kind of the opposite of weight. And I also know I have my coefficient of friction is given in the problem, which is 0.250, which has no units on it. And then I can actually solve for that, and we can figure out what the force of friction is. So 1,960 times 0.25 gives me this frictional force of 490 newtons. All right, we're getting close here. We're getting close. I have this kind of map figured out, and so I'm going to put this in as 490 newtons. Now, you'll notice that they cancel out in the up and down 1960, but in the left and right, they do not cancel out. I've got 1,500 newtons to the right and 490 newtons to the left. So what is the total force on this object? If I was to redraw this kind of free body diagram with just the total force on the object, here's my crate again. And my gravity and my normal force cancel out. So they're not there anymore. And my force of friction and my applied force don't cancel out entirely. And what I'm left with is an applied force that is less than it used to be. In fact, it's 490 newtons less than it used to be, right? So my total force here is to the right, where I can go ahead and say, hey, 1,500 newtons minus the 490 newtons, which is in the opposite direction. So kind of the sum of all of my forces over here is 1,010 newtons, right? That's the sum of my newtons or my forces in the x direction. And I can go ahead and plug that in right here and say that this is 1,010 newtons in the x direction. I've just subtracted whatever my kind of force of friction was from my original pull here overall. So this is my new kind of free body diagram with all of the forces, the sum of all of the forces. This is it. And in fact, my last kind of piece here is to say, well, I want my acceleration. And my acceleration, the definition of acceleration is the force that's being applied to something that we call the net force, the total force, and dividing by the mass. Well, actually, I know these things where I've got this net force here of 1,010 newtons, and my mass was given to me in the problem of 200 kilograms. And so now I've got it. I've got everything that I need. I just need to take that 1,010 and I need to divide that by 200 kilograms. And if I do that, I'm going to walk away with my acceleration. And I'm getting a little tight here, so I'm going to slide up just a titch. And I'm going to go ahead and say that my acceleration now, my A, is equal to 5.05. What units do I have with this? Well, acceleration is always going to be in the units of meters per second squared. So my final answer to this problem is this answer right here, is that that block is going to accelerate to the right, or that crate is going to accelerate to the right at 5.05 meters per second every second. It's going to speed up by 5.05 meters per second every second. All right, there's a lot going on in there. I know I kind of spread things out a little bit in this. I worked in the margins a little bit. I annotated the problem up at the top. So there's a lot going on here, but this is what I've got. All right, I hope that helped you, and I will see you in the next one if you'd like to watch it. All right, take care, everyone. Bye-bye.